Yesterday, my third period left off on this slide, and my fifth period finished this slide. So if you're in fifth period, skip ahead to the next problem. But for my third period, this is another piecewise function, and we evaluate piecewise functions by looking at the limit from both sides. So when I look at the limit from the left of 2, that means I'm looking at numbers less than 2. So this is that second equation right here. Now, if I actually plugged in 2 like we did in the last example, you'll notice that I'll get an undefined in the denominator because 2 minus 2 is 0, and that's a problem. So I have a vertical asymptote here on this problem, which means that I can't actually plug in 2. I have to plug in a number that's a little bit smaller than 2. So I'm going to choose, and I'll write this on my paper as well, the limit as x approaches 2 from the left-hand side, and I'm actually going to choose it to be 1.9. So if I plug that into the bottom equation, I get 1.9 minus 3. Divided by 1.9 minus 2. Now with that known, the numerator, I really don't care what this equals, I just care whether or not the whole thing simplifies to a positive or negative number. So 1.9 minus 3 is a negative number, and 1.9 minus 2 is also a negative number. Excuse me, a negative number, which means that this simplifies to a positive, and therefore, as it approaches 2 from the left-hand side, it follows the vertical asymptote up towards positive infinity. From the right-hand side, I have the limit as x approaches 2 from the positive numbers, which means that I'm looking at this top function when x is greater than or equal to 2. And you'll notice that the same thing happens. If I try to plug in 2, I approach another vertical asymptote. So I need to figure out if it approaches it as it goes towards positive infinity and goes up, or towards negative infinity and goes down. So if I plug in a number that's really close to 2 from the positive side, I'm going to plug in 2.1 in the numerator and 2.1 minus 2 in the denominator. So the numerator is equal to a positive number, and the denominator is also equal to a positive number. So this one approaches positive infinity as well. Because both the left and right-hand limits approach positive infinity, we can say, therefore, the limit as x approaches 2 of this function, f of x, is equal to positive infinity. Next example. Example 11. This is the example that all of us should be on. We did not do this one in class yesterday. This is the last example from evaluating limits algebraically, where we will look at rationalizing the numerator. So normally we rationalize the denominator, but in this case we're going to rationalize the numerator in order to help us make this not an undefined term anymore, not an undefined expression. Because if I plug in 0 to the numerator, I get 0 plus 2, which is the square root of 2, minus the square root of 2, and that gives me 0 in the numerator. And if I plug 0 into the denominator, I also get 0. So I have 0 over 0, and therefore we know that we're going to need a trick, or one of our strategies, I should say, in order to simplify this problem. So here's how you rationalize the numerator. We are going to rationalize it by multiplying it by exactly what you see in the numerator, x plus 2 under a square root, except the only thing I'm going to change is I'm going to make that a plus instead of a minus. And that's going to help me to rationalize the numerator and get rid of these square roots. In the denominator, I have to multiply by the same thing, because whatever you do to the top of a fraction, you also have to do to the bottom of a fraction. Oops, that should be a 2. Alright, so that's what we get here. When we multiply out this binomial in the top, we have our first terms, our outside terms, our inside terms, and our last terms. So let's write that down here at the bottom. We have the limit as x approaches 0 of, when I multiply the first terms together, I get the square root of x plus 2 times the square root of x plus 2. That's just x plus 2. My outside terms, I'm going to get the square root of x plus 2 times square root 2, and the inside is square root of 2 but negative times the square root of x plus 2. So you'll notice that it's exactly the same term, only one of them is positive and one of them is negative. So we've actually set up a difference of squares here. And the nice thing about that is that those middle terms will cancel each other out, and I don't even need to write them. So then let's look at the last term. We have negative radical 2 times a positive radical 2. So that gives me a minus 2. Radical 2 times radical 2 is 2. In the denominator, you're actually going to notice that I'm not going to multiply anything. I do not want to distribute this x into this binomial, because if I do, it's going to mess up everything. And every single time you do a problem like this, you should always leave them unmultiplied. You should leave them in factored form, because you'll notice in the next step that that x is going to simplify to 1 with an x we find in the numerator. So from here, if I simplify the numerator, I get x over x times the square root of x plus 2 plus radical 2. So now look here. I have an x in the numerator and an x in the denominator that are going to go and simplify to 1. So I'm left with a 1 in the numerator and I'm left with the square root of x plus 2 plus radical 2 in the denominator. Now, if I would have multiplied that x into this binomial up here, notice that I would not have been able to see this cancellation as easily, and definitely you want to leave it unmultiplied and leave it in factored form because that will always happen. At this point, if I evaluate the limit at 0, I can now use direct substitution to take 0 and plug it into this function everywhere I see an x. So that gives me 1 over the square root of 0 plus 2 plus the square root of 2. And if I simplify that, I get 1 over radical 2 plus radical 2, which is 2 radical 2. So that's 1 over 2 radical 2. Now I know that this technically is not rationalized, but the AP test does not care about rationalization, so we're going to leave our answer like that. Now let's move on to the new topics. Today we're going to find limits algebraically, so I'll give you a minute to write this down. The extension of this, we won't have a warm-up today since I'm not here with you guys, but it says I will algebraically evaluate limits at infinity. So in our last one we were dealing with limits to infinity where we had vertical asymptotes. Today we're going to look at limits algebraically at infinity. So now we're going to have the limit as x goes to infinity. So I'll let you guys write these down really quick. This is just a summary again of the rules for horizontal asymptotes. So it says when f of x is written as a rational expression, or in other words, a fractional expression, a is the degree of the numerator and b is the degree of the denominator. So these are the rules for horizontal asymptotes. If a is less than b, then as we go towards infinity, we have a horizontal asymptote at 0. If a is greater than b, as we go towards infinity, the asymptote would not exist because the function would either go forever up or forever down. So we'll figure out if it's positive or negative infinity in that case. And last but not least, if a is equal to b, then the limit as x approaches infinity would be the coefficient of the numerator divided by the coefficient of the denominator, the leading coefficients. So again, these are just the same as the horizontal asymptote rules. So let's do this first one together. I am looking at the degree of the numerator, which is x squared, and the degree of the denominator, which is x cubed. And if you remember from our last slide that hopefully you just wrote down, if the degree of the numerator is less than the degree of the denominator, there is a horizontal asymptote at y equals 0. So therefore, as I go towards infinity, my graph is going to follow that line. So therefore, my limit as x approaches infinity of this function is equal to 0. My graph is going to follow the horizontal asymptote. And that's my final answer for that one. Next problem. For this one again, we're looking at degrees because I'm looking at the x goes to infinity. Anytime I think of x goes to infinity, I'm always, let me go back one slide. Anytime I'm looking at x goes to infinity, I'm always trying to find a horizontal asymptote because I know my graph will follow that horizontal asymptote as it goes towards infinity. So that's why we're looking at horizontal asymptotes in this example. If I look at the degrees, I have a degree 3 on the top, a degree 3 on the bottom. Therefore, because they are equal, I'm looking at the ratio of the leading coefficients, which in this case happens to be 4 divided by 5. So my limit as x goes to infinity is 4/5. And that's because it has a horizontal asymptote at 4/5, and the graph will follow the horizontal asymptote as it goes towards infinity. If you need a little bit more convincing about that, you can graph this function on Desmos, and you'll see the graph following the line 4/5. Let's try this example. We have x cubed in the numerator and we have x in the denominator. Therefore, the degree of, the degree of the numerator is greater than the degree of the denominator. So what that means is that there is no horizontal asymptote. So our function either, let's look at our two scenarios, our function either goes up forever or it goes down forever. So that's really all we need to figure out. As we go towards positive infinity, are we following the limit up to positive infinity or are we following the limit down to negative infinity? So here's how you figure that out. We're going to plug in a number as, I guess as big as you want it to be, but we're going to look at whether or not it's positive or negative. Again, I really don't care what the number equals as long as I know whether or not it's positive or negative. So if I look at the limit as x goes to infinity and plug in a number that's big, let's just use 100. I have 3 times 100 quantity cubed minus 23 all over 4 times 100 minus 1. Oops, that's kind of an ugly 100. Minus 1. Again, this number I just pulled out of thin air. All I know is that it's a big number, and I kind of doubt anything crazy is going to happen on the other side of 100. So I think I've chosen a big enough number to get a pretty good idea on whether or not this function is growing bigger or growing smaller towards positive or negative infinity. 100 cubed times 3 is a very, very large positive number. If I subtract negative 23 from that, it's not even going to make a dent. It's not even going to make a dent in that number. So this numerator is definitely going towards a positive value. In the denominator, I have 4 times 100 minus 1. And again, 400 minus 1 is definitely a positive number as well. Maybe not growing as rapidly as the numerator, but that just goes to show you that it's going towards a huge number on the top and maybe a smaller version of that on the bottom. So we have a positive divided by a positive. Therefore, this is going towards positive infinity. And I can say that the limit as x goes to infinity is also going towards positive infinity. Now you may see that sometimes on an AP test or an assessment. They might write do not exist, does not exist, but typically they write either infinity or negative infinity. So we evaluated at a large number to determine that it went to positive infinity, not negative. All right, let's try another example. For this one right here, the easiest way to solve these problems is probably to get rid of the complex fraction. So if you remember how to get rid of a complex fraction, the easiest way is to multiply by the common denominator. So I'm going to multiply everything by an x on the top and everything by an x in the numerator and denominator. So when I simplify that, I get the limit as x approaches negative infinity. And then when I simplify here, I get 4x squared minus 5x cubed plus 3x. That's just from me distributing the x into the numerator. And then in the denominator, I get 1 over x times x, which happens to just be 1. And now essentially I've gotten rid of this complex fraction and I only have a polynomial now. So if you look at this polynomial, the highest degree is x cubed, so it's a cubic function, and the leading coefficient is negative. So if I was imagining the graph of this polynomial, I would imagine that it would look something like this. So it's a cubic function, which gives it this S-like shape, and it's negative, so it goes in the opposite direction. It goes up to the left and down to the right. Knowing this, if I'm looking at the limit as x goes to negative infinity, just follow the graph with your finger. As it goes towards negative infinity, it goes up and up and up and up and up. That's going towards a positive infinity. So my limit, therefore, is equal to positive infinity. Great. Let's look at this one. The other ones have been pretty self-explanatory with looking at the horizontal asymptotes and also looking at this last example where we had to look at what was happening in terms of a polynomial function and simplifying the function first. This example is a little different because you might not know what the graph of a square root function looks like, and you might not be familiar with the rules of finding horizontal asymptotes like this as well. So let's briefly talk about it. I hope you agree with me that the square root of x squared, is going to give me a x. The square root of x squared is x. So when I'm looking for the degree, I'm going back to my rules for horizontal asymptotes. If I'm looking for the degree of the numerator, I look at the highest degree that's underneath the square root, and then essentially I just square root it. So if I have an x squared, the square root of x squared is going to give me x. So I know the degree of my numerator is x to the first power. Well, my degree of my denominator is also x to the first power. So my degree of my numerator and the degree of my denominator are the same. So hopefully you go back and you remember the rules for what happens if we have our degrees the same, and it happens to be the ratio of the leading coefficients. So in the numerator, I have the square root of 1x squared, so the coefficient in the numerator is a 1. And in the denominator, I have this 2x. So I have a 1x essentially over a 2x. So really, my ratio is 1 over 2. But in order to figure out if it's going to be a positive 1/2 or a negative 1/2, because these problems actually create two asymptotes. I'll show you in just a second. I'll type it into Desmos. They actually create two asymptotes. So to figure out if you're going to be following the positive or negative asymptote, we look down here at what we're going towards, which in this case happens to be infinity. And I'm going to look down here and I'm going to say 2 times infinity plus 1. That's going to be a positive number. And the numerator always has to be positive because it's under a square root. There's no way that square root's going to be negative. So the numerator will always be positive. When I plug in a positive infinity in the denominator, I also get a positive. So that means that as we go towards infinity, it's going to follow the 1/2. It's going to follow the 1/2 asymptote. So this is going to be equal to 1/2. And then let me graph it right now and I'll show you how there are two asymptotes when we have a problem like this. Alright, so here's what a graph of this looks like. It's the square root of x squared minus 3x over 2x plus 1, and you can see it kind of looks funky. We haven't really ever seen a graph like this, but there's some weird thing happening here in the middle, and then there's kind of a gap down here in these numbers, because if I plugged in anything between 0 and 3, you'll notice that I'll get an undefined answer for the numerator, so obviously I can't have anything there. And then I have an asymptote over here at -1/2 from the denominator. So like I said, there's a lot of funky things happening. But what I wanted to show you is that if, depending on how far out you go, so let me zoom out really far, if you kind of look at these y values over here, the bigger and bigger I get, notice that my y values are getting closer and closer to -0.501, or essentially -0.5. So I could go out even further and you'll see it gets pretty close to -0.5 to the point where that's what the limit is going towards. So as I go towards negative infinity, notice that my limit is going to a -1/2. And as I go towards positive infinity over here on the other side, notice that my limit is going towards a +1/2. So it follows two different asymptotes depending on which direction you're going. And that only happens when we have these square root problems like this. So if I'm going towards negative infinity, it follows -1/2. If I'm going towards positive infinity, it follows the +1/2. And that's just this example. They change. So in order to make sure you're looking for the correct one and actually finding the correct answer, always make sure to plug in infinity into the denominator to see if it's going to give you a positive or a negative answer. Our last example is this one, and it's actually the exact same example, but this time we're looking at the limit as x goes to negative infinity. So my degree of my numerator is still 1 from the square root of x squared. The leading coefficient is still 1 because the square root of 1 is 1. In my denominator, my degree is also 1, so the degrees are equal, so we're looking at the ratio of the leading coefficients. My coefficient is 2, so I'm looking at a 1/2. And then remember, I'm just going to plug in a negative infinity here to see whether or not I'm following the +1/2 asymptote or the -1/2 asymptote. So if I plug in negative infinity, I get 2 times negative infinity. That's a ginormous negative number. If I add 1 to it, it's not even going to put a dent in it. So the denominator is going towards negative. It's going towards a negative value. And remember the numerator, because it's underneath a square root, it's always going to have to be positive for us. So I don't even have to worry about the numerator. The denominator will determine whether or not it's going towards the positive or negative asymptote. So in this case, because we're plugging in negative infinity, it goes towards the negative asymptote, which happens to be -1/2. And that's my final answer for this one. Alright, you should be able to do all of your homework now to the best of your ability. There are a few that I know are more challenging than others, so if you get stuck on some, then please just bring questions back to ask me on Wednesday. But at this time, I want you guys to turn off this video, and I want you to do as much of that homework assignment as you can in class. Whatever you don't finish in class, you can finish at home, and then bring me questions back tomorrow on Wednesday. Alright, have a great day.